Hello everyone, this is in continuation with my previous video when I discussed about mutually exclusive and disjoint events. This video I'm going to talk about addition theorem of probability. So this is how the addition theorem of probability is defined. If A and B are two non-disjoint or non-mutually exclusive events, that means A and B can happen at the same time, then the probability of happening of A or B can be given by probability of happening of A plus probability of happening of B minus probability of happening of A and B. And the symbolically, if you use set theory, it can be written as probability of happening of A union B is equal to probability of happening of A plus probability of happening of B minus probability of happening of A and B. A intersection B, you can use it as an intersection. There is a little proof which you can do to this particular theorem. It has been asked. So I'll take the left hand side, probability of happening of A union B, that can be given by number of favorable cases of A union B divided by total number of cases, where S is representing the sample space, and that further can be, the numerator can be written as number of elements in A plus number of elements in B minus number of elements in A and B, or A intersection B. That means the members which are in common divided by total number of cases here. This further can be written as, using simple algebra, a little distribution, and number of elements in B divided by total number of cases, number of elements in A intersection B divided by total number of cases. Now this simply becomes the formula of probability of happening of A plus probability of happening of B minus probability of happening of A intersection B, and that is exactly the right hand side. So this is a little proof which you can do. I can also talk about a little bit about that how this numerator has been obtained, but let's first talk about that how if what if I'm going to take a case here. If A and B are disjoint, or they are mutually exclusive, are disjoint or mutually exclusive, then what is going to happen? So if A and B are disjoint, then I know that probability of happening of A and B is actually equal to 0. That I have discussed in my last lecture, sorry. So that is going to be, the theorem now is going to get modified simply to probability of happening of A union B is equal to probability of happening of A plus probability of happening of B, because probability of happening of A intersection B is 0. So that is how the theorem gets modified if the events are disjoint or mutually exclusive. So that's how the theorem gets modified. And so I need to see whether whatever type of question I'm dealing, whether the events are mutually exclusive or not mutually exclusive. If they are not mutually exclusive, then you're going to use this particular part, or equation number 1. If the events are mutually exclusive, then you're going to use equation number 2. So that is a little bit about addition theorem of probability. If you're confused that how I have written this particular numerator, it is pretty simple to understand. If you see that there is a set A which has, let's say, 2 4 6, and okay, it's not working there. Let me write it little at the bottom. So A is a set which has 3 members, 2 4 6. B is a set which has members, let's say, 2 and 3. So how many elements are there in common? There is only one element in common, which is 2. So if I look into number of elements in A, they are 3. If I see number of elements in B, they are 2. And if I look into number of elements in A intersection B, they are exactly 1. And if I look into number of elements in A and or B, not and, it's or, A union B, then it is actually how many? 2 4 6 3. I cannot write 2 times, so they are actually how many? 4. So if you look into the thing, number of elements in A union B are actually number of elements in A plus number of elements in B minus number of elements in A intersection B. That simply is 3 plus 2 minus 1. So that becomes 4. So that's how this numerator can be written. Now let's see if the theorem gets extended up to 3 cases. That means if you have 3 not mutually exclusive cases, then how probability of happening of A union B union C is defined. That's how it has been defined. You can check this particular formula. I'll not be discussing this one in detail. This is just for the reference. Let me do a question now. If a card is drawn at random, then what is the probability that the card is a red or a king? So let's do the first part. Let's say event A is defined as card is red, and event B is defined as card is a king. So in a pack of cards, I know there are 2 red kings. One is a king of diamond, other is a king of heart. So there is a possibility that if I take a card out and it comes out as a card of diamond king, then it is red also and it is king also. So that means these two events are not disjoint. So I have to see whether the events which are defined in the problem are the disjoint or not. Are not disjoint. Or you can simply say they are not mutually exclusive. That means they can happen at the same time. So if the events are non-disjoint, then simply probability of happening of A or B is given by probability of happening of A plus probability of happening of B minus, this is minus, I just need to correct it, I'm sorry. Okay. Minus and probability of happening of A and B together. So A is about red card. There are 26 red cards and total 52 cards are there. Plus there are B is a king, so there are 4 kings and there are in total 52 cards. And there are 2 red kings only. So that's how the probability is going to be. If you calculate it, this is going to be okay, 28 by 52 and it's going to be 7 by 13. Let's see the second part now. The second part. Now I'll say event A is card is a king. That is the outcome. And B is that card is a queen. Since these two cards are different from each other, that means they cannot happen at the same time. It's not possible that you pull out a card and it is king also and or it is a queen also. So and it is a queen also. So it cannot happen. Simply. So A and B in this case here, in the second part of the problem, are disjoint. Or you can simply say they are mutually exclusive. If they are mutually exclusive, yes, I know it very well. The theorem is going to get modified a bit. If they are mutually exclusive, let me just explain a bit. Then probability of happening of A and B together becomes 0. And that is going to be probability of A plus probability of happening of B. And I know there are 4 kings, so 4 by 52. And there are 4 queens, 4 by 52. So that is going to be 8 by 52. It's going to be 2 by 13. That's it. So that's how the addition theorem is applied, and that's a little example of the things. and what I'm going to do is I'm going to discuss more examples on addition theorem probability. Thank you.